to the class. Calculus 1. Unit 1 is limits and continuity, basic differentiation. All right, limits and continuity, you may or may not have a ton of experience. The continuity part you should have seen before, whether you're good at it or, kind of a different story. Limits, it's often one of the first topics to be cut out of pre-calc when time is short. So you may not have seen that. It's kind of like what I was talking about last time with trig. Sometimes you get the short version. Right, so I'll take you through that from the ground up. Basic differentiation. Unless you've taken this course before, you probably don't have too much experience with that. All right. So in order to really understand limits, you need to have a good sense of how to create graphs. Now, some graphs you don't really have to think too hard about in order to create. Like if you had an equation of y equals x squared, if you didn't know how to graph that by hand, you just pop it into a calculator. It's usually the easiest thing to type in, or easier thing to type in. And then just take a look at the picture and just pop that down on paper. I wanted to focus on the weird ones, like piecewise functions and absolute value functions. All right. The absolute value functions, they could be pretty easy too, but oftentimes people struggle with finding the correct notation on or in a calculator. So I'll first show you how to do all this stuff with Desmos, and then I'll show you how to do it using a TI calculator. Well, I have a TI emulator, so it's very close to a TI calculator. It's not quite exactly the same, but it has the major components all in the same place. Right. So it's an old in-class problem where the do now problem. State the domain in interval notation and determine any asymptotes. All right. Now, in a pre-calc class, you might have had to do this by hand. I don't know. It depends on the class you took. Depends on where you took it. All right. I always encourage my students to try to think about a graph before they dump it into a calculator, just because if you develop any kind of familiarity with a function, it's probably going to come through a technique along those lines, right? Whereas the folks that always go right to typing it in, they know how to get a graph. They don't necessarily know why the features of the graph are the way they are. All right. So let's start off with the domain. Just a quick review. When you're talking about domain, the two things that you want to keep in mind, at least at this stage of the game, is we don't want the equation to be undefined, and we don't want it to be imaginary. So do not want undefined or imaginary. All right, we don't want undefined or imaginary. Poor quality or, let me just fix that real quick. All right, the only way an equation is going to be imaginary is if there's a radical involved, so I'm not worried about that. All right, so what I'll do is I'll set the denominator equal to 0. And solve. This will be the excluded value. All right, possibly more than one excluded value. So in this case, there's only going to be one excluded value. All right, so if I set my denominator equal to 0, my denominator is just that good looking X right there. I'm going to take that, set it equal to 0, and solve. Well, it's already solved, so I'm not worried about that. All right. So what that's telling me is that X is the X equals 0 is an excluded value. So this needs to be out of the domain. So not included in the domain. All right. So when I think about a domain in interval notation, I wouldn't just say X is not equal to 0. Interval notation is the one with the parentheses and the brackets, if you remember. All right. So parentheses, exclude the given value, brackets include, All right, the brackets include the given value. All right. Something else to consider is that parentheses are always the fencing used for infinity. All right. So fencing is just the umbrella word for parentheses, brackets, squiggly brackets, anything like that. All right. So we can say fencing because it's fencing in the values. All right. So what we're saying here is that in my domain, we're going from negative infinity to infinity, but along the way, we're going to exclude 0. All right. So I'm going from negative infinity, or quality infinity, not much better, to infinity. But along the way, we're excluding 0. So let's go from negative infinity to 0, but not include the 0. All right. We're also not going to include the negative infinity because it's infinite. Well, you can only include finite values. You can only capture a value if it's capturable. Right? Infinity is always on the move. Right? If I say the biggest number is 1,000, you might say, okay, well, no, it's 1,001. And somebody else says 1,002, and so on and so on and so on. Every time you take a step closer to infinity, infinity takes a step further away from you. All right. So because it can't be captured, it gets parentheses. All right. So we would then want to pick up on the other side of 0. So what I'll do is I'll start with 0, but not include it. All right. Now, the big concern that comes along the way here, students have this, and it's a question that comes up every class that I teach that involves domain, and every semester I teach it in. All right. Could I just start off with a 1 with a bracket? That's what the question the student asks. And the answer is no, because then you're not including all of those important numbers between 0 and 1. All right. If I were to say, oops, that's not a marker, 1 to infinity, everything between 0 and 1 would be excluded. All right. And we need them to be included. All right, because there are finite, I'm sorry, finite, I keep wanting to say finite. There are infinite values in between integers. Right? There are infinitely many values in between 0 and 1. So to exclude them, you're excluding a form of infinity. And I'm just gonna make this a little smaller. I'm gonna make a little notation here. Not the same as that. All right, and I'm going to put a little U. U without the tail stands for union. All right, and that's because we're uniting those two sets. All right, so it's not just one set and the other set separate from one another as if they're two different functions. They're two different domains, essentially, that form a single function. All right. So it would be incorrect to say that the function has two domains, negative infinity to 0, 0 to infinity. It's more like the single domain has two components. All right. It's just a little slight change in the wording, but it is very important. All right. So all that was just for domain. All right. Well, now we got to get into the asymptotes. All right. So we have 3 types of asymptotes: the vertical asymptote, the horizontal asymptote, and what we call either the oblique or the slant asymptote. All right. The vertical asymptote is pretty easy to identify. If it doesn't present itself visually, it'll present itself algebraically. All right. So for the vertical asymptote, VA, set denominator equals 0 and solve. All right. There is a little condition to this though, and this is where people kind of fall by the wayside, and that's not a good thing, obviously. If you can factor and simplify your function, you would need to do that before you set your denominator equal to 0 and solve. All right, so all of this is assuming that the function is already in simplest form. All right, so I can make a little note of that. I'm going to resize a little bit here. Lost the part of the colon. Assumes function is simplified. All right, because if you can factor and cancel, that might actually open a different can of worms. You know, you might be looking at a point discontinuity, or otherwise known as a hole in the graph. But you're not. Let's say you go through the process and you solve for a vertical asymptote and you're just not sure. You're like, oh, I don't know if this function's simplified or not. You just take a look at the picture. Right? You just look at the graph and see if there actually is a vertical asymptote at, in this case, it would be x equals 0. Right? I'll write down all the answers in a second. Right? Horizontal asymptote, that's the most involved one. But it's kind of funny. Maybe, you know, like you won't find it to be funny, but I'll say it's interesting. Horizontal asymptotes are going to get easier as this unit goes on, because once you realize that the concept of a limit actually helps you find a horizontal asymptote, then the rules that I'm about to lay out for you, they become irrelevant. So it's kind of like, oh, well, then why bother with the rules? It's circular logic. You have to know these rules in order to understand the concept of a limit. But once you understand the concept of a limit, you can disregard these rules. And it's almost like, okay, well, I'm done with those rules. I don't need them anymore. So it's tricky, but you know, like in the sense that you kind of have to believe that I'm not lying to you. But if you do, then there's a payoff at the end. All right. So horizontal asymptote, we look at the highest power of the numerator and the denominator. Those are called the degrees. The degree is the highest power in any kind of polynomial function. All right. So what we would want is the degree of the numerator to either be equal to or less than the degree of the denominator. If it's greater than, then there is no horizontal asymptote. All right. So the degree of the numerator has to be less than or equal to the degree of the denominator. Shrinky dinky coming right up. This is bound to be a source of aggravation for many of you. And what I mean by that is I start writing and then it becomes clear that I'm going to run out of room, and then I just shrink it down. And you're like, well, that's great for you. What about the rest of us? I don't have that answer. Write small or get the good notes out, or whatever app, you know, something that would be helpful. So the horizontal asymptote will exist if the degree of the numerator is less than or equal to the degree of the denominator. But we got to look at them individually. If the degree of the numerator is less than the degree of the denominator, then the horizontal asymptote is the line y equals 0. All right. This is all stuff that should have been covered in pre-calc, and I don't see how the course would have progressed if it wasn't covered. So it's definitely covered. Just a question of whether it was emphasized or you retained the knowledge. But if this looks like, whoa, I've never seen this before, it might be a matter of just kind of going back and looking at attendance and seeing if maybe you were absent that day. Maybe you were late that day, because it might have been covered in the first 5 minutes of class. I don't know. Right. So if the degrees are the same, then the horizontal asymptote is the ratio of the leading coefficients. All right. So in this case, we have no horizontal asymptote. Right? Because the degree of the numerator is not less than the degree of the denominator. The degree of the numerator is not equal to the degree of the denominator. And the way I know that is the degree on top is 2. The degree on the bottom is a 1. All right, that's the highest power on the bottom. All right. So there is none here. I'm going to go green for those keeping score at home. The horizontal, the vertical asymptote is the vertical line x equals 0. All right. Now, the third type of asymptote is actually irrelevant in this case. All right. Oh, actually, I'm sorry. I was thinking of something else. If there is a horizontal asymptote, then there is no oblique or slant asymptote. So if the horizontal asymptote exists, then the oblique or slant becomes irrelevant. I got my wires crossed there for a second. So for the OA or SA, depending on how you learned it, what you like, oh, that's fun. The degree of the numerator has to be exactly 1 more than the degree of the denominator. All right. So degree of the numerator is equal to the degree of the denominator plus 1. All right. So then, unfortunately, there isn't a quick rule of thumb for this. It's more of a process. To find the oblique or slant asymptote, you're going to divide the numerator by the denominator and drop any remainder. All right. So this is a lot of stuff you're taking on faith. If this doesn't sound familiar to you, then this is like, oh, you just make up whatever you want in math. Oh, this is fun. Math just got easy. I could just do whatever I want. Everything's going to be fine. Because this one just seems like it comes out of nowhere. But there is a limit justification for why this works the way it was, or the way it does. Right. So divide. I almost wrote dividend. Divide numerator. Divide denominator. And drop the remainder. All right. So I'll just kind of do that off on the side here because you don't really need a whole heck of a lot of space. You can do it with long division, but because on the bottom we're looking at a monomial single-termed expression, this is actually pretty easy to divide. All right. So, and what I mean by a remainder is if you were to use long division or synthetic division, you might end up with a remainder value. But when you actually carry out division, that gives you a fraction. All right. So it's basically saying drop any fraction that remains as part of the expression. All right. So that's great because that's telling us to drop whatever might make it difficult. Sorry, I gotta clean this up. It looks terrible. I got to the end of the screen. I tried to squeeze it in there, and it just didn't work. All right. So what we can do is split the fraction. So this would become f of x equals x squared over x minus 1 over x. Remember, when you're breaking up a fraction, you can break it up according to a positive or a negative. So a plus or minus in the numerator only. So you think about getting a common denominator and putting two fractions together to make one. This is splitting the numerators, but making sure that each numerator has that common denominator. Right? If I were to go the other way and put this together, I'd get back where I started. Right? Simplify. And then drop any fraction. The 1 is the remainder, so that would get dropped, but along with it comes the over x part of it with the minus. All right. So my OA or my SA, we would ditch this piece, would just be the line y equals x. All right. So that's like a straight 2 units worth of pre-calc in one problem. That's a nice way to get a course started, right? You might look at that and say, whoa, that's pretty intense. I look at it and be like, these are the things that I've noticed over the years that people needed the most review with. Like this is the stuff that, like went by the wayside once the semester was over for most. Some people remember it like it was yesterday. But if you're going to forget anything, it's probably going to be these like little fine details. So I thought it was worth the time. But let's take a look at this in a calculator. First, we'll do Desmos, and then we'll go with the TI. All right. If you're going with Desmos, you could actually type it in pretty much the way you see it, which is great. You see the little ABC in the lower left-hand corner. If you're using a full-blown computer, the display looks a little bit different, but it still has the same ingredients. If you click on ABC and then type in F, then go back to 1, 2, 3. Some people are already like, I don't like it, but it takes a little getting used to. But once you get used to it, it's pretty intuitive, right? Which I guess is the opposite of being intuitive. So f of x, close it up. It asks you if you want to add a slider. I don't, because I'm not taking some constant f and multiplying it by the variable x. I want to create a function. So I'm going to type in equals. Now, if I want to put a fraction in, I want to put the fraction in first. All right. So I'm going to hit divide to create the fraction. Then I'll type in the numerator and then the denominator. And then you see a function appear. Nice looking graph. All right. Very vibrant in terms of colors. Stands out on the screen. Some people don't like the little boxes there. You can play around if you go into the little wrench. You can play around with the setup. If you want to turn the grid off, you can. That's up to you, though. That's a personalization part of it that is entirely in your or at your discretion. All right. So what I'm going to do is I'm going to type in the asymptotes. All right. So the first one is x equals 0. Now you can see here that the graph doesn't exist at x equals 0, but I really want to emphasize that. So what I'm going to do is long press on that little icon on the left-hand side, and I'm going to make that dashed, just so it shows up as not part of the graph. All right, because it's very easy, especially when you start putting multiple graphs on the same set of axes, it's very easy to think that one connects to the other, when really it's two separate graphs, and this is just a boundary. Now, if you're unsure, you can bring it in, zoom in, just a pinch zoom, and just keep going until you're satisfied that they're not going to touch. Once you get out to around like 20, you should be pretty satisfied, but some people aren't. So you keep going, keep going, keep going, keep going, keep going. I'll get up to 100. Another way to do it is to zoom out a lot, then I'll go up to 1,000 actually, and then zoom back in later on and see if it, no, you see it's still not connected. You really got to zoom in order to see that, but it's really not connected. Now, I don't want to have to zoom my way back out, so I hit the little home key there, and that brings me right back to -10 to 10, which is great, because I didn't want to have to, go through that whole process, all right? We had no horizontal asymptote, but according to my calculations, y equals x is a slant asymptote. All right, so same deal, long press on it and make it dashed. Now, again, if you've kind of forgotten what an asymptote is, you just think of it as a line, and there are other types of asymptotes that aren't lines. So that's different conversation altogether, right? But it's for our purposes, a line that your graph will approach, right? So your curve will approach these lines. Now, it's very important that you don't, in your mind, finish that thought with "but never touch," right? Because so often in the past, and it's incorrect, it'll be taught as it's a line that a graph, an asymptote is a line that a graph approaches but never touches. That "but never touches," that part is incorrect. All right. The only type of asymptote that you cannot make contact with is a vertical asymptote. And the reason you can't make contact with the vertical asymptote is because the graph is undefined at that location. It doesn't exist at that location. There is no graph there, right? So it could never actually get to that x value, because if it did, it would be contradicting itself, right? That's the only instance. Horizontal asymptotes can be intersected by curves. Same thing with oblique asymptotes, but it's really about how it behaves towards the end. All right. So what we call that, very shockingly, end behavior. Right. As you go out for extreme values of x, so as we go out to the right, how does the graph behave? Now, if you look at this, hopefully you recognize that the red curve and the green curve are virtually indistinguishable from one another. If this graph could get out to infinity, the f of x function would be no different from the y equals x function. It'd be exactly the same. They will have merged to be the same graph, right? They will have connected, right? So what that gives us is an avenue to make predictions about complicated functions using much simpler functions. So you kind of look at it and say, well, if I need to go out to large values of x, I can just think about the y equals x graph. So if somebody said to me, all right, okay, so let me give you a function. F of x equals x squared minus 1 over x. What do you suppose f of 1,000 is? I would say it's 1,000. About anyway. And it's like, why do you suppose that? Well, because its end behavior is y equals x, where y and x are the same thing as one another. Right? I could actually just put in, let's say, f of 90, just because it's on my screen. F of 90 is about 90. Now, f of 1, that's not the best example, because f of 1 is equal to 0. If I plug in a 1 for x in the original function, I'll get a 0. But for large values of x and y become indistinguishable from one another. So if I did f of 900, you see it's even closer to being 900, 9,000, and so on, until you get high enough where it rounds virtually to that number. So they become indistinguishable from one another. And that is the power and benefit of an oblique asymptote or even a horizontal asymptote, because for the predictive power to be able to make or draw a conclusion about a function for large values of x without having to worry about the funky, nasty function, you can work with a much simpler. All right. So hopefully that was all explained in pre-calc. It doesn't always end up being that way. I know I taught pre-calc for so many years, 15 years or so, while I was teaching calculus and and statistics and everything. So I always looked at the intersection between the courses and how they kind of related to one another. And there's so much carryover from a course like pre-calculus into statistics, where people don't think, well, I'm taking statistics, for example, so I don't have to take pre-calc. But you can actually see a lot of the pre-calc in a lot of the math that you tackle down the line if you're looking for it. All right. So let me just show you quickly on the TI. The app that I use is the X84. It's very good in the sense that it emulates the TI calculator very well, but there are some differences. I think they had to throw in some differences. One, in order to make it jive with touchscreens, but also just so I guess they didn't get sued. But it's good. I like it. The X84 is free, but if you want more advanced features, you got to pay a little bit. It might be $5.99, but an emulator calculator for $5.99 is still better than the real deal for like $150. So that's where my brain always takes me. Anyway, if you have a TI calculator and you wanted to create a graph, you would hit y equals and get rid of this stuff. So I have this equation. You could use the numerator over denominator function. I'm just going to use parentheses. So x squared minus 1, close it up, divided by just an x. I don't need parentheses for that because it's a monomial without any other additional factors. Redundant. All right. Now, if I want to look at the picture, I can do it a couple of ways. If you're using a handheld TI calculator, you could do it by hitting zoom 6. All right, so that's the standard zoom. And what that'll do is give you an ordinary negative 10 to 10 window. All right, because this is an emulator, it doesn't bother with zoom, because if you hit graph and you don't like what you see, just pinch zoom until you get what you do want. All right, and so this is what I'm looking at. I had another stack graph up there. I'll get rid of that at some point, but this is essentially what the graph look like. TI calculators, for whatever reason, they don't, they're not really good when it comes to vertical asymptotes. I honestly think it has to do with some really significant flaw in the programming, where they just can't get around the idea, or the calculator can't get around the idea that you need to draw the entire graph from the left side of the screen to the right side of the screen without picking your pencil up off the paper. So it's like, all right, well, I need to draw this curve, so let me start off. I'll go up. Well, there's no other way to get to the bottom of that screen without drawing a line to get down there, so I'll do that. And then continues on the way, and it includes a vertical asymptote. And my younger students, my high school students, sometimes they can't get around that. They can't get that out of their head. So on paper, they'll draw that vertical line as if it's part of the graph. And it's like, well, it's not. It's incorrect. All right, but you can see a lot of the same features. I mean, it basically does what Desmos does, just not as well. I'm a TI basher right now. Honestly, I think it would be a lot friendlier towards TI calculators if there was some sort of advancement. I'm working with the same TI calculator now, essentially, that I did when I started my career over 20 years ago. There have been minimal advancements, but yet the price is still the same. So it's kind of like I'm just bitter now. Right? So if you're kind of looking at it like, this guy won't shut up about the TI calculators and why he doesn't like them. That's a little bit of a taste of it. It's very unfair, and I don't care for that. That being said, I'll stop blabbing about the TIs and I'll always show you the Desmos version and the TI version. But we don't have to go too crazy here, because you can see it's got all the same stuff that the Desmos calculator showed. It's a verification that there is no horizontal asymptote. And the way we know that is it never levels off horizontally, right? If it leveled off horizontally, kind of like a log function, if you remember those, then we would be looking at something that has a horizontal asymptote, but it doesn't do that, right? It does merge or start to merge with a slanted line, and it does approach a vertical line. So you know to be on the lookout for a vertical and an oblique asymptote. There is a contradiction between horizontal and the slant asymptotes, the oblique asymptotes. If one exists, the other won't. So once you identify that a horizontal asymptote exists, for example, then you know that the oblique or slant won't, and vice versa. All right. So just something to keep in mind. If it seemed like I'm spending way too much time on one problem, how are we ever going to finish the course? A lot of the time, I will get locked in on a particular type of problem because it's that important. I don't want to gloss over anything, but then you'll see that we'll just be like, okay, and this one you just chuck in your calculator and move on. All right. So if you're starting to get a little nervous, I would say let things unfold a little bit before you start panicking. Please don't panic. I'm gonna get the, oh, look how much nicer that is. But again, I will show you the TI stuff just in case next semester with another teacher, they're saying you got to use a TI and there's no ifs, ands, or buts. All right, so for a piecewise function, this is a graph that is exactly what it sounds like. It's a graph that is basically in pieces. All right, so you know it may not have sounded exactly like that, but what it's telling us to do is graph this piece for this domain to start. So we're going to graph y equals, let me get it a little thicker there, the marker. Y equals 2x squared on the domain of 0 to infinity. Now, this may seem unnecessary what I'm about to do, but I'm going to write this in interval notation for two reasons. One, because I think that if you're not strong with interval notation, you can never get enough practice early on. And once you get it down, it becomes second nature. The other is, I think it does a good job of telling us where to start the graph and where to stop the graph on paper, right? But I'll leave it up to you. This is the kind of thing where I wouldn't need to see the work on a test, right? I would just need to see the answer, right? So this domain, x greater than or equal to 0, means that we're starting at 0, going to infinity. We always put parentheses on infinity because we can never capture infinity. Infinity is always on the move, always on the run. It's the elusive reptile. Little Mortal Kombat reference. Mortal Kombat. The TI, so the question in the chat was the TI shows the XY values. Does Desmos do that? The answer is yes, and I'll show you how to do that in a couple minutes. Good question. Very good question. All right. The next piece would be y equals 2 minus x. Now this one is all values of x that are less than 0. So that means we'd be going all the way down to negative infinity. All right, but maxing out at 0, but never getting to the 0. So parentheses on the 0. All right, so just to talk about the idea of a table real quick, what you would do is tap on the little plus sign. If you're ever in doubt about how to get started with something on Desmos, you can tap on that plus sign and it might get the juices flowing in terms of what the approach ought to be. F of x would be an expression. You can select that, but that's the default anyway. You could put a note in there, right? So that's if you want to type in letters, but you don't want them to be representative of variables. I'm sorry, constants. But what we want to do is create a table, all right? So the default settings for a table is X1, Y1, because it's always treating it as ordered pairs, and it needs to distinguish between different tables. If I created 10 different tables, I wouldn't want to always refer to the same X value. But in this case, I'm only going to make one table. Now you see here, I changed that, and I'll just show you real quick. If I put in a table, you see X1, Y1. So I changed the column headings just by overwriting it. I changed it to X and F of X. All right. Now you see here, F of X is now represented by a red set of points. That red corresponds with the function F of X that's in red. All right. So any point that's going to come up here is going to correspond with F of X. So what I would just do is type in the X values that I'm interested in. So let's say I want negative 10 to 10. I type in negative 10, hit enter, type in negative 9, hit enter, and then Desmos will assume the next value in the pattern. It realized that I'm going by increments of 1. And so it says, okay, you probably want negative 8 because you just did 2 consecutive values. So let's give you the next consecutive value. And then so you can just hit enter, 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 keep hitting enter until you populate it through. All right, I'll do negative 10 to 10. Now you see here, all these points now show up on the graph. You don't need to actually have it show up on the graph. You could just tap on that little scatter plot diagram to make it disappear. But these are the coordinates that you would get if you evaluate F of X, the F of X that we typed in over here, for these particular X values. And you can change them as you go. The thing that Desmos won't do is auto-populate a list for you like the TI does. But most of the time in the TI, you're hunting around for the appropriate X values. It's really no different than just typing in a few and hitting enter a bunch of times. It just takes a little bit more. So hopefully that answered your question. And that's a good kind of segue into how we're actually going to approach graphing these two pieces of the piecewise function.
I'm sorry. I'm sorry.
Sure.
I just missed the part where you showed us how to do the graph. Can you show it again? Like the first step.
Wait, say it. Sorry, say it again.
I said, can you show me the part where how to like show the graph on Desmos? I missed that part.
You're talking about the points that I just created, or?
Yeah, like how to get the graph with the whatever equation we put in.
Oh, you're talking about the F of X?
Yeah.
Oh, okay. Yeah, you just type it in. So I'll show you real quick. So if you were typing in F of X equals X squared minus 1 over X, you type in F of X equals, then hit the division key to create the fraction, X squared minus 1, and then tap into the denominator and then just type in the X. Yeah, you're just typing it in with the keyboard or keypad.
All right, thank you.
No problem. All right, so what we're going to do now is actually the same idea, except we're going to use 2x squared and 2 minus x. Now, they're parabola. It's a parabola and a line. So you could very easily do this by hand, but I want to show you the technique so that when you're given a function that's not quite so easy, you can do it. I mean, hopefully you get my reasoning there, you know, because a lot of folks would be like, well, couldn't we just do this by hand? It's like, it's not, I'm not teaching you so that you know how to do this problem. I'm teaching you so that you know how to do the problem that's 100 times more challenging using this technique, all right? So what we would do is type in y equals 2x squared. Oops, missed the 2. That's your parabola. Now there's a couple of ways we can get some coordinates, but if we only want the relevant points, then we could do this one of two ways. We can create a table corresponding to the domain, or we can use, it's a little fancier technique, but it's very doable. It's really up to you. One way is pretty easy. The other way is a little bit more involved, and you might kind of look at it like, I don't want to do it that way. I totally understand. All right. So what we're going to do is create a table. with X values and Y values. Let me get rid of that. I'm going to move this up. Oh, you know what? Sorry. I confused myself. We have to call it something. F of X, G of X, Q of X, doesn't matter, but we got to call it some function of X. The reasoning there, and it might seem a little wishy-washy, is that for some reason, Desmos has a default understanding of, well, Y could be anything. You know, like Y could be an equation. It could be itself a variable. So it has this restriction when it comes to Y, right? But for whatever reason, it doesn't have the same restriction when it comes to F of X, and I haven't figured out why yet, right? But it's not too difficult to just say F of X instead of Y. Now, you might look at this and say, well, we already have F of X, which is the original function. Well, then call this one G of X. You know, just the next letter in the alphabet, right? So then 1, 2, 3, get a bunch of points. Obviously, we're not going to plot all of these, but it'll give us the relevant points necessary to plot in this graph, right? And if I want to, I can say, you know what, let's turn the parabola off by tapping on the icon and just focus on the coordinates themselves. These are the only things that should end up on paper because these are the only ones that are consistent with the domain, all right? So I'm going to plot 0, 0. Now, very important, that 0, 0 corresponds with a bracket, all right? On a graph, we plot that with a closed circle, all right? When it comes to parentheses, we plot that with either an open circle or arrow. All right, open circle if it's a finite point, arrow if it's infinity. Right, so basically, it's only going to be an arrow if you're dealing with infinity. Otherwise, it'll be an open circle. All right, so I'm going to plot 0, 0, 1, 2, all coming from my table. I'm going to do it in blue. 1, 2. Now 2, 8 is going to go off the screen, right? So I'm not really keen on doing that. But what I can do, unless you want to get into scaling the graph to go by 2s, but you're really only doing that so you can get one more point in there. I don't think that's worth it. We know that this is supposed to be parabolic. Don't make it a line. Give it a little bit of a curve and you're good. I didn't do such a hot job there. So what I'll do is I'll use a sticker marker and then there we go. All right. So that's one piece. The other piece is Y equals 2 minus X. Now, this is what I was talking about before when I was saying that you can save your work on Desmos, hang on to the work that you've created. What we just created is kind of like it's very short, but it's like a master sheet when it comes to plotting a piecewise function, right? Because now what I can do is I could just change this 2x squared and make it a 2 minus x. And you see everything else changes along with it. The only issue is I need to go from negative infinity to 0. So I want to change my table up a little bit here. So maybe not even negative 10. Let's do like negative 5, negative 4, negative 3, negative 2. And you can delete all the other stuff. Negative 1, and then end off at 0. And then all this other stuff goes away. Just put the appropriate values in. I don't even need that negative 5 because it's going to be off the grid. Negative 4 is going to be off the grid. But the negative 3 will give me a 5. So I can plot that. Negative 3, with a 5, -2 with a 4, -1 with a 3. But then that last one, okay, so we got to be careful here. Open circles or arrows. That's what you're going to get when you have parentheses. All right, open circle or arrows. So in this case, in the case of the negative infinity, we're going to get an arrow. But in the case of 0, that's not infinite. So that's going to get an open circle. So at the coordinate 0, 2, I'm going to plot an open circle. And that would be my piecewise graph. Now, if you have experience with piecewise functions, you may recognize the function itself as being improperly formatted. You should always have the negative part of it first. So the part where the domain is negative or less than the other part. So these two are actually swapped. This is a typo that I've had for a long, long time. I just never got around to fixing it. It should be the other way around. All right, so just a reminder, when it comes to typos, in order to get the bonus credit, all you have to do is send me an email, and that email should contain the page or the location of the typo and what the typo is. And if it's not obvious, how to fix it. You know, in this case, you could just say the piecewise typo on page, what is this, 3? On page 3, and that would be fine. But remember, it's first come, first served, right? So there's going to be many instances where you submit a typo and you don't get any bonus for it because other people beat you to it. But eventually, you know, you'll start getting your points once everybody else is maxed out. And you know, if you're a little slow on the draw there, you'll be able to pick it up. It's a maximum of 3 points per unit. All right. So once you get 3 points, you don't need to submit it. All right. Now let me show you how to do this using a slightly different approach on Desmos than again with the TI. All right. So let's get rid of this. I'm going to take it from scratch here. All right. I'm going to say f of x. Well, you know what? I'll be a little bit nicer here. I'll use g of x equals 2x squared. And I'll take h of x is equal to 2 minus x. All right. I'm going to be a little bit more precise with how I build this one because I'm going to save this and put it up on Blackboard once Blackboard is up and running again. All right. So what I'm going to do is I'm going to put a little note here. And that note is going to say where G and H are 2 pieces of function. Actually, I'm going to say just are the pieces. F. All right. Something to keep in mind. If I say F or if I say F of X, I'm saying the same thing. Also something that should have been discussed in pre-calc. Hopefully it was. I don't want to assume the worst, but I've had to explain some things before. I'm also going to give this a title, piecewise graphs. And then I'm going to slide this up. So it's the heading. All right. Now, what we want to do here is we want to institute the domains because you'll see here on my Desmos, I have a whole lot more than I need. And it doesn't give me anything with open circles. All right. So there's a lot of stuff going on here. All right. The open circles, I mean, there's a way that I can kind of build that into it, but it kind of depends on you to recognize when it should be an open circle or not. I'll get to that in more detail in a second. But what we're going to do is open a squiggly bracket. So in parentheses, open a squiggly bracket. after each piece. All right. And now that I think about it, let me just take a second and reverse these. I'll call this one H and I'll call this one G. Because like I said, with that typo, it should have been the other way around anyway. So for consistency with the way it's going to end up being, that's what I'll do. All right. All right. So again, this is all going to be saved for you anyway. But if you're following along, I just made that little adjustment. I switched the order. If you need to change the ordering of things, all you got to do is long press or click on the icon on the left side of any command line and just hold it down while dragging. All right, and you'll see that the blocks move. All right, and then you can replace them wherever you want. Now, if you put something substantial into your Desmos and you're like, oh, I don't want to have to type that in again, that's when you start thinking to yourself, I better save this. So I had that little menu bar, go to save, and I'll call it Piecewise Graphs. Man, this guy's spending an awful lot of time on piecewise graphs. Just imagine, just flash forward to the first unit test where a question, and it will say, find the limit of this function, and it'll be a piecewise function. To know that you have a calculator that's going to do all the work for you, that's pretty nice. Right? So what I'm going to do is open a squiggly bracket. I'm going to say x is greater than or equal, in this case, 0. Then you can just hit enter because it'll automatically, if it opens a squiggly bracket, it'll automatically close it. But if you feel the need to close it yourself, you go into the QWERTY pad again, so the ABC, and then hit the up arrow to go from left squiggly bracket to right squiggly bracket. Right, and then close it that way. But you'll see, I'll just show you real quick. If I hit enter, it locks it in anyway. But every time in Desmos, every time you hit enter, it creates a new bar. If you don't want that, just X it out. All right. So then squiggly to open. The next one is X minus 0. X minus 0. X less than 0 is what I meant to say. All right. Now's the fun part. I want to make this so that it's user-friendly for any situation. All right. So that's one thing. Another thing is it didn't tell me anything about endpoints, whether it's open circle, closed circle, or what have you. So what I'm going to do here, if you long press on the graph, you see it gives you an indication of the point. When you get to the very end, you'll see that that point has now become an open circle. And that's because the graph is undefined at that location. Now you might say, well, it's not undefined. In the do now problem, we had to set a denominator equal to 0 to see that it's undefined. We didn't have to do that here. It's undefined because of the way this piece of the function is defined. X cannot be equal to 0, right? Because the domain says X is less than 0, not equal to 0, right? For the red piece, right? Whereas if you're on the blue piece, long press, you see all these points, all these points. When you get to the end point, you see it's a solid point, right? So you get to the end point, you see it's a solid point, and you have something to plot, right? Why does that not look like my picture? Because I put my domains in backwards. Okay, well, anyway. I'll use a technique I like to call the right way, but you get the idea. This is what it should look like. But if I go down the line here, open circle, you now know to plot an open circle. All right. Closed circle, when you drag it along the line, even if you're using a mouse, closed circle means plot a closed circle. All right. So that's a little nifty little piece there. Now, something else to consider. Maybe I want to make this even more user-friendly. All right. So what I'll do is I'll type in a little note. All right. Another way to type in a note would be to use quotes, although I can't seem to find them here. So if you're using a keyboard and you want to type in open quotes, it'll automatically bring the notation part of it in. But what I'm going to say is replace G, G, and H with your piecewise, oh, pieces, yeah, that works. I'll say piecewise pieces. A little best of both worlds there. And when I save this on Blackboard and you've created an account, you look at this and say, well, that looks stupid. I'm going to change that. Go ahead and change it. Once you save it, it's yours to keep. All right. It won't change my master copy. All right. Now, what I'm going to do is I'm going to replace the 0 with the letter A. You'll see it says add slider. I'm going to tap on that. I'm going to change this to B because there's no guarantee that the two pieces will coincide at the same X value. Maybe the first one will be less than 1 and the second one will be greater than 5. So I'm going to create a slider for that one too. So you know what, maybe I'll just leave it where it was. All right, so now what I can do is I can slide my slider and make the graph as long as I want, depending on what my actual A value is from the problem. Now, when I use a touchscreen, you see this happens, it just kind of hops on me when I pull my finger off. If that happens, just go in, just tap on it and type the number in, and it'll understand what you want to do. All right, so you could slide or you could actually type the number in. And now I have something that's a little bit more user-friendly when I go to apply this to a different question. So now I'm thinking about a question where it might say f of x equals the sine of x, and the other piece is the natural log of x. I can just replace the 2 minus x and the 2x squared with those two pieces and slide my slider wherever I want it to go, and I'm good. All right. There are exceptions. You know, there are instances where that won't necessarily work out. But at least this is something to get you started. I save it, and then later on, I post that onto Blackboard in the Unit 1 calculator folder. All right, so that's yours to keep. All right. Now, the last thing that we're going to talk about tonight, it'll just take a minute, is the absolute value function. All right. So absolute value function, I'm going to create a new graph. F of x equals 2. You see the absolute value bar right next to the comma has a little A in it. Just tap on that. If you're using a keyboard, just it's right above enter, shift, and that backslash key. If you hit shift, that backslash key gives you a vertical line. That's also absolute. All right, just type in x, close it up, and then -3. All right. You could drag along to see the points if you don't want to create a table out of it. If you do want to create a table out of it, you're welcome to do that. But if you see that when I tap on the graph itself, 3 gray dots appear. Those are very important dots. Desmos will always point out to you, if it can, any intercepts and any turning points. So if you really want to know what those values are, you tap on it again. The -1.5. It has symmetry, so the other one you can assume is +1.5. And then 0, -3. If you have the vertex and one additional point in an absolute value function, then you have enough to create the absolute value function itself, because just like a parabola, you're going to have an axis of symmetry, and you're going to have equal distance from the left and the right for any point. All right. As long as you have the vertex, you know where it flips around on itself, you're good to go. And so this is my absolute value function graph. I can get a straight line drawn. So now you see what it looks like when I draw a line by hand versus what the app will do for me. I have nerve damage, so my lines come like in all shapes and sizes. It's actually pretty good, but it'll straighten out for me. So that's one of the reasons why I use the app here. All right. Now, just a quick refresher. The standard form for an absolute value function is f of x is equal to a times x minus h plus k. A is the slope. HK is the vertex. If A is greater than 0, it opens up. Opens up? No, opens up. If A is less than 0, it opens down. All right. So if you like standard form models, and there's a time and a place for that, we'll get into that as we go forward. That would be pretty useful for you. You might recognize that as being very similar to a parabola's standard form equation. Just instead of x minus h as an absolute, it's x minus h squared. Right? But that's the rule itself. All right. So what I'm going to ask you to do, it's not really homework. It's just kind of advanced preparation for the next class. Is just to take a look at the next 2 pages. All right, because I want to hit these pages in the beginning of class. I'll put a star on both of these pages as a reminder for you to look at them. If you don't end up trying them, that's fine too. But the idea is that you'll have at least had a look at them before you come into class next time, so that we can hit on these concepts when we get into continuity and then and discussion of limits. All right. So if you're still writing, I'm going to bring this back for you, but I wanted to switch over real quick and take attendance. Normally I would do that in the beginning of class. Yeah, the domains were swapped. Very good. Normally I would do it in the beginning of class, but I didn't.